by request an elementary introduction to Lee groups, and I really do mean elementary, and I make no apology. If you've seen it all before, sit back and relax. My first lecture today is just a very simple look at Lie groups and their associated Lie algebras. The second talk is going to be on Lie group actions and their infinitesimal vector fields and why we love them. And the third talk is on Noether's theorem. So that's what Noether's theorem, smooth and discrete. So that's kind of where I'm heading. And there are enormous volumes and textbooks written on Lie groups, and some of them are very scary. And so I'm a practitioner, and Lie groups to me appear in the applications. They appear as groups of transformations which are of interest to the physics, or which leave a certain object invariant, or almost invariant, in particular a differential equation or a Lagrangian. And the application for leaving a Lagrangian invariant is Noether's theorem. And there are algorithms for calculating these Lie groups, and often they're not Lie groups as I'm going to define, they're local Lie groups. They're only defined in neighborhoods of the identity of some Lie group, but they still, nevertheless, because my point of view is that of a practitioner, this is going to be more of a practical view about how to calculate. So, all right. The typical examples of Lie groups and how they arise are as, so this is how they arise in practice, as groups of transformations. And I'm going to move back to the main model of a Lie group as a manifold in a minute. But we have translations, rotations, and shearing transformations, and Möbius transformations. And you can see that the second two are sets of matrices. And the S means special, which means that the determinants are all one. And as groups of transformations, the product is always composition of functions, composition of transformations. But Lie groups have the property that they're not finite, and they're infinite, but they're not discrete. So they're infinite and smooth. The group elements depend smoothly on parameters, which I'll make more in a minute. And the fact that the composition of two of them still ends up in the set, induces a composition law on the parameters, and it goes like that. Okay, so first of all, so number one, they're groups. So just to remind you of the definition, we have closure, associativity, identity, and inverse. If you're in a matrix group, then the only possible identity is the identity matrix, and then you have to prove that that identity matrix is in your set. And I'll show what associativity means later. I seem to have this twice, several times. No? Closure. Okay. So, no? Where are we? Oh, never mind. I thought I fixed this. Okay, so let's look at this very basic little group, which is just it appears as a rotation group of rotations in the complex plane, and the product, as you can see, that the product is just simply a sum of the parameters. So this is kind of like, it's associative because the sum is associative, and so on and so forth. So I've really spelled out here what associative means, and the reason I spell it out is because the Lie algebra is not associative. So it's good to have be clear in your mind what does associative mean. It means that it doesn't matter how I construct the ultimate product. I can multiply those two together, multiply those two together, then multiply those together, and then multiply that. And as long as I maintain the order, I can rearrange the brackets, and that's what associative means. All right, So a Lie group is also a manifold. So if we look back at our beginning examples, here the manifold is self-evident. Here the manifold is the unit circle in the complex plane. And this turns out to be a rather complicated manifold, which is defined by these equations here. And you can work it all out. So this is a manifold defined as locus of algebraic equations. All right. So to be a manifold means that about every point we have coordinates. And the really only important coordinates are the coordinates about the identity, because if I want coordinates about any other point, I can simply take my coordinates about the identity and I multiply. I can right multiply or I can left multiply, and that gives me coordinates around my other point. And the requirement is that product and inversion are smooth maps. And the big deal about Lie groups is that we can do both algebra and calculus. And this is the real power of a Lie group. This is where the power resides. I'm not talking loud enough. I need my microphone. Okay, so they were found and used by Sophus Lie. And I'm really tired of students mispronouncing Lie. So I have a little pronunciation guide to Lie, and he found them as smooth transformations of ordinary differential equations which map solutions to solutions. And he discovered that all of the known methods for the exact integration of ODEs, in particular the various methods to reduce an ODE, to change coordinates, in which the ODE is solvable by quadratures, all relied on the fact that there was a Lie group symmetry. And these Lie groups, when you're given an ODE or you're given a Lagrangian, the Lie groups that you get don't look like the ones in the textbooks. They look like what you get in the coordinates that you're given. So I'm interested, so it's very good to have a native understanding of what these things are, so that when you're confronted with your particular Lie group, you have an idea what to do. So essentially, these transformations are a smooth so supposing you have an ODE in one dependent variable. So then so basically they're smooth transformations on your XY space, and given this, you can, by the chain rule, induce an action on all of the derivatives, and the second derivatives and the third derivatives, and it's this what's called a prolonged group action is what you're trying to solve for when you want to change. So you want to change coordinates to make your ODE integrable, and right. So this is what you've got to do. So you get your smooth transformations, and if there's a finite number of real or complex parameters, then you have, in general, a local Lie group. So that means that you have a Lie group whose parameters are in a neighbourhood of the origin, and the group action may blow up on the edges. But often, okay, so, and it's easiest, so it's normal and it's good to study Lie groups which are subsets of the general linear group on some field for some dimension n. In other words, the matrix Lie groups, and that's the easiest and the best way to first start with Lie groups. Occasionally you do get that your smooth transformations leaving your PDE or ODE invariant depend on functions and arbitrary functions, and typically these satisfy a differential system. So the number one example the number one example is to area preserving diffeomorphisms in the plane. And if you, so there the differential equation, so you've got one transformation for your x coordinate, one transformation for your y coordinate, and then the differential equation that they satisfy is that the Jacobian is 1, identically 1. So that's the Lie pseudogroup. So unlike for Lie groups, which now have this very rigorous and firm foundation as being both a manifold and a group, there's no equivalent theory for a pseudogroup. And the theory of Lie pseudogroups has been studied by world famous mathematicians who famously never wrote the second volume because the theory got too hard. And so but some people, some very good people like Peter Olver, think that the concept of a manifold, that what is the underlying model that you should study, is actually the involutive system of PD that they satisfy. So we don't have an object that we can say. We only understand Lie pseudogroups through their shadows, which is how they act on certain spaces. But the Lie groups can be studied as an object in themselves, free from any transformation. So that's the difference between the two theories. Right. So here's a very elementary example of two Lie groups with the same manifold but different products. So here the manifold is the cylinder. So we have both of them have a rotation, and both of them have an R2. I've only drawn a two-dimensional cylinder. It's a three-dimensional cylinder, sorry. But the two group products are very different. On the left we have the direct product, and you can see that the translation part, in order to have a matrix representation, I've changed the matrix part to a multiplication. And on the right we have a semi-direct product, and these are not the same. They are completely not isomorphic as groups, because on the left it's commutative and on the right it's not. So they can't be isomorphic. Okay, so I thought I would, so I'm treading on dangerous ground here talking about SO3. There are as many understandings of SO3 as there are people who use it in their applications. And this is, and you see this when you realize how many definitions of different coordinates and how application dependent they are. So I've written up the three coordinates as though you were doing navigation in an aeroplane. And so these are coordinates that are travelling with the aeroplane. So this is actually like a moving frame. However, so the reason that there's so many coordinates is because there are kind of no good coordinates really that help everybody, and no global coordinates are possible, and the manifold looks very complicated. So let's have a little look at the manifold. So SO3, I should have pointed out that SO3 is defined by matrices whose inverses are their transposes, and also the determinant is 1. All right. So let's have a look at the manifold. The manifold, you can understand the manifold. I always think of it as thistledown, you know, like a dandelion seed head. So you've got the axis, and then around each axis you've got like a little twirl of your angle. So you can think of it as a two-sphere cross an S1 sphere divided out by the fact that we have this little problem that rotation and that rotation are the same the same rotation. The only element of the rotation group that doesn't have an axis and an angle is the identity element. So we have all of this in the identity element. All right. So a much better way to work with SO3, and this is the way that I've always used it, is what I call the Cayley representation, and this is the name comes from where I learnt this from a book of German physicists. But I understand there are a lot of other maps called a Cayley map, but this is mine. And the difference about this Cayley map is that this is actually a representation of the group. So we start off. So here we start off with another group called SU2. This is the special unitary group. So the S means the determinant is 1, and the unitary thing means that the inverse is the conjugate transpose. And you can prove that the 2 by 2 special unit, the 2 by 2 elements in this group all have this form, and where alpha alpha bar plus beta beta bar equals 1, and this is the determinant equals 1 condition, and this other condition is guaranteed by this configuration. And you can see that alpha, if you consider the alpha and the beta the real imaginary parts to be the parameters of the group, then it's clear that this is the sum of the squares is 1, and that this is a much nicer manifold. This is S3. So this is the unit sphere in R4. And this is, and I've left it for a little exercise for you to prove that first of all that that's the general form, and also that the, oh, I haven't given you the image yet. Well, the image, what I'm going to have is that it's a representation, it respects the product, but also it's 2 to 1. And so this is quite good, because remember that our rotation, that our idea about axis and rotation was also a 2 to 1. So here it is. So this is, I typed the transformation into Maple in order to prove to myself that this was a representation, and did everything I wanted, because you can see it's quite complicated, and I always test things to prove that I haven't made a typo here. So this is guaranteed. So first of all, if the sum of the squares is 1, then this is guaranteed to be an SO3, and you can prove that. And I will show you in a little bit where this comes from. It looks rather magical. So why is this so great? Why is this representation of SO3 as an image of SU2 so wonderful? The reason that I like it so much is because if you give me an axis and an angle, I can give you the element in SO3. That's why I like it. So I have a lot of problems where I'm trying to solve for an element in the rotation group. I need a rotation that goes from there to there, and this tells me how I can do it. And I can also very easily work out, that's obviously an isotropic group. I can go from there to there and then do anything around there. So this gives me this has been a very practical way for me to find the group elements of SO3 and use them in my application that I've needed. In fact, if you look around lots of people's representations of SO3, they are actually SU2 in disguise. For example, quaternions, or low order Clifford algebras and rotors and things coming from there's a lot of names for them. They're essentially quaternions and Clifford algebras, and all of their versions of SO3 are in fact SU2 in disguise. All right. So Lie groups have both a local structure and a global structure. The global structure, so any manifold has a global structure. Any manifold has coordinate charts, and there's a pattern. So you take the coordinate charts and you look at the pattern of the intersections of the intersections, the intersections of the intersections of the intersections, and that gives you what's called the check cohomology. Because this is a manifold, the check cohomology is the same as the de Rham cohomology, and so on and so forth. And you can actually prove that there's an elaborate construction for a group cohomology, and that's the same as the group cohomology. So anyway, you can study the global structure and the pattern of how the coordinate domains overlap, and also, of course, obviously the number of components that you have. The local structure is what I'm going to talk about next. The local structure is essentially all that we can solve for. If you want to say that this differential equation, that this group transformation that takes this equation to this equation, that is a non-linear condition. But we can only solve for the linearized condition. And this brings in the Lie algebra. So there's a lot of competing definitions of the Lie algebra. There's the right invariant vector fields, the left invariant vector fields. I've got my definition means that if I meet a Lie group in a dark alley and I don't know what it is, and it's operating on some weird space, and I really don't, and of course nothing that I find in my travels, or few things that I find in my travels, look like any of the Lie groups that are listed in the textbooks. So I have to have a way to find the Lie algebra that's guaranteed to work. So this is my method, is that I simply take a path through the identity and I differentiate it. And provided you can differentiate it in some coordinate system or in some scheme that I'll show you, then you can calculate it like that. And if you can't do that, then you have to use a more sophisticated method, which is as equivalence classes of curves through the identity. But that's, I'm not going to go there. But let's look at the Lie algebra. So on the left I've got the Lie group, and that dot there is meant to have the identity, that's meant to be labelled with the identity. And I'm simply going to take the Lie algebra as you give me a smooth path through the identity such that gamma of 0 equals the identity, and I differentiate it at t equals 0, then the collection of those paths is the Lie algebra. That's a working definition which definitely works in the dark alleys of the various applications. So all right, so it's the tangent space of the Lie group at the identity. So as long as this d by d, as long as this makes sense, then you can do this. So if I have a matrix group, then to differentiate a path in a matrix group, the derivative is calculated component-wise, and I can use the product rule. So here's my SO3, and I've got two conditions, and I simply take a path. What's the path in the Lie group? Well, it's a of t. T goes to a of t, and this is my identity. This is an identity for all t. If I do d by dt at t equals 0 of both sides, take into account that a of 0 is the identity, then I get that. So this is how to derive the famous fact that the skew-symmetric matrices at the identity is the Lie algebra of SO3. I have a second condition, which here is redundant. In fact, if I differentiate the determinant, I get the trace. But it's redundant in this particular case. So this is how to derive this famous result. Okay, so a tangent space at the identity for any manifold is a vector space. So one structure that we have on the Lie algebra is that it's a vector space. But I have a lot more structure on it. So let's look at this adjoint map. You give me a fixed element in my group, then I have a map from G to G given by conjugation, like that. This essentially is a change of coordinates about the identity, and it respects the product, like that. So what's so great about this conjugation? Well, if I take a path through the identity in my matrix Lie group and B is any other element, then this is another path through the identity, and that means that I have and it turns out to be a representation of my Lie group on my Lie algebra given by this. And so you guaranteed, so you give me something in my Lie algebra and B is any element in my group, you're guaranteed that that is back again in the Lie algebra. And because my Lie algebra is a vector space, I get a matrix representation, and this is called the adjoint representation. Alrighty, so let's look at our running example. Here's SU2, and so what is the Lie algebra of SU2? Well, you know what to do now. We take our condition, we differentiate it at the identity. I get that the alpha dash of 0 has no real part, and this is free because there's no condition on it. So this is my Lie algebra. So now, let's take an arbitrary element, and you see where I'm headed now. Let's take an arbitrary element in SU2, and lo and behold, I get the Cayley map. So that's where the Cayley map comes from, and that proves that it's a representation because it's the adjoint representation. And that's a really nice exercise to do that. And you can see how I feel about it. Alrighty. Alright, so now let's do, so this is an exercise for you, is to do this for SO3, and what you get actually is that after some effort you get that the adjoint representation of SO3 is itself. Yeah. And it's because if I write my Lie algebra in a particular way and I act on a vector, then it's essentially the cross product. That's what it is. So if you unwind all of that, and the adjoint action for SO3 on its Lie algebra is the identity is itself. Takes an element to the same element. Alrighty. So now I've got this wonderful adjoint representation. And now I'm going to, so this is how you find the bracket. What is your bracket? You've got a Lie group and a dark alley. You differentiate it. When in doubt, differentiate. Pass through the identity, and you've got the Lie algebra. But it's still not obvious what is the bracket on your fancy Lie algebra in some fancy strange space. So what do you do? Well, you take your adjoint representation. The x is fixed, but now I'm going to take a path through the identity for my b, and now I'm going to differentiate this. So this is a path in G through x, this thing here, and because this is a vector space, I can conflate the tangent space at x with the tangent space at, well, anyway, you get that this is in the Lie algebra. So this is what you get. So this is how I derive brackets in strange situations. And for the matrix bracket, it gives you exactly what you want. So in the simplest situations, from here you get that the derivative of the inverse is this, and because b passes through the identity, I get this. That has to be in the Lie algebra, and so I get that this matrix bracket is in the Lie algebra, and this is true for any matrix Lie algebra. So you see, it's not I always like to see the proofs of these things, because I need to be able to adapt my proofs to other situations where I don't have a matrix, or I'm in some very strange I don't know, principal fiber bundle on some surface and some whatever. But anyway, so far I've got that the Lie algebra is a vector space. I have a representation of G in a set of invertible linear maps from G to G. I have a skew-symmetric bilinear bracket which does this, and there's one more important property which I'm going to show you how to do it now in a bit, obviously. So the next slide isn't the Jacobi identity. So we have a couple of fun things. So the fun things are the bracket table, and these are objects of meditation. They are so beautiful. These Lie algebra bracket tables are just so beautiful, and it's really good to be able to do them. And we have what's called little add of x. So capital add of x was what you did with from the group to the Lie algebra. Now a little adjoint is simply this map here, which is the bracket like that. That is a linear map from G to G, and these linear maps are the key to success. Understanding these linear maps. And the entire Cartan classification of semi-simple Lie algebras comes down to studying these maps here, so this is a very good thing to have under your belt. So this particular map has an important property. So I'm restricting still to matrix Lie groups because this is the first thing that you should look at to really see the line of argument that you get. So I take now another path through the identity, C of t, and I notice that this adjoint on this one goes through, it goes into the bracket simply because it can. If I now differentiate both sides of this equation with respect to t, and I set d by dt at t equals 0 of ct to be z, I get that. And that's the quick and dirty proof of the Jacobi identity, and that's the proof that can be adapted to all kinds of situations, is looking at this. And yeah.
You didn't say it, I don't think. The little adjoint is the linearization of the big adjoint.
Yes, it is.
That's why C prime of t is Z, I guess.
I've set C prime, yeah, so that's just like a notational thing because I've already used X and Y. Z was the next letter, but yeah. It is the linearization of the adjoint, yes. That's exactly what it is. But I mean, the proof of it is because that adjoint map goes in and out of the bracket. Yeah, so if you're looking to prove an analog of a Jacobi identity, you have to have that. Alrighty. So if you actually look at this, what do I have? I had that add of z on this goes through like this. And in other words, add of z is a derivation like the product rule. So this is, or the Leibniz rule. So this is what's called the Jacobi identity. All right. So I now have I have a formal definition of a Lie algebra, and the big thing is, if you look at this Jacobi identity, you'll see that it shows that the Lie bracket is not associative. So it really does matter how you do the brackets. And so in an algebraic proof using a Lie algebra, wherever you would normally use the associative law, you have to replace it with that. So here's just a little example of a bracket. This is SL2. So I was extremely fortunate to be taught Lie algebras by Georgia Benkert at Madison, Wisconsin, and she was a student of Jacobson, who wrote one of the first really serious textbooks. And she gives these names to these basis elements, and I'm not going to change them. So here is the Lie bracket table, and you can see that add of h bracket e is 2 of e, h bracket f is minus 2 of f. That little add of h is diagonal, and the secret to the classification of Lie algebras is finding the ones which act diagonally. And that's why the classification is over C, not over R, because over C you can always find eigenvalues and eigenvectors of these little maps. And so I'll leave that for you while I find the next my next set of slides. This says that the Jacobi identity yields this. Here's the add of the bracket, it's the bracket of the adds. So what is this? This is the matrix bracket. So in other words, add takes the bracket in the Lie algebra to the matrix bracket. In other words, it's a Lie algebra representation. So I'll now find my next lecture. And we start on what is it? Control L. Okay. So I hope that was a very elementary introduction to the kinds of things that we're going to need. And we're now looking at Lie group actions. I'm going to have a glass of water, a bit of water. Alrighty, so this is the Möbius transformation. So this is an action of SL2 on either the real line or the complex plane, but you have to add the element of identity in order to have a well-defined act to get an action of the whole group on the whole space. So it works like this. And the actions satisfy a very important property, which is if I act on one and then I act with another one, it's the same as acting by the product, like that. So you can reverse H and G and then you get a right action, but I'm doing everything for a left action. And don't get me started on left and right. So all right. So as I mentioned before, if given an action on the plane, we induce an action on curves, surfaces, and their tangents. And the induced action is always via the chain rule, like this. And I've drawn you a pretty picture, like that. Yeah. So, of course, this group action can interchange, can mix and match what is the independent and what is the dependent variable. And it's amazing how many people I've had to teach the chain rule to for these kinds of situations. Alrighty. So here's the fabulous application, is Noether's theorem. So this is the simplest part of Noether's theorem. Noether's theorem is actually two theorems, and they're both if and only if, and they're much more sophisticated. Normally we only see the cut down version. They're more sophisticated than the cut down version, but anyway, here's the simplest one. The simplest one is that, so the underlying idea is that the Lie group symmetry of an action principle gives a conservation law. That is the fabulous application. And what does this mean? It means that the entire integrand, including this volume form here, you have to transform the volume form according to the chain rule, just the way you normally would. And that has to equal that. And this integral sign can mean, under equivalence classes, with respect to divergence. So in fact, it's not just that the integrand goes to itself, but you can add a divergence. Okay, so the underlying mathematics of Noether's theorem is that if this is equal to that for your diffeomorphism group, then you get a divergence expression which is 0 on solutions of the Euler-Lagrange equations. And that theorem is completely constructive. And if you look at in Peter Olver's textbook, I think that the statement of it for arbitrary order and arbitrary numbers of dependent variables, I think just to state the recursion formulae for the divergence expression runs for some pages, and then the proof runs for a lot more pages. But it's the kind of thing that computer algebra can do for breakfast. So here's the other fabulous application, which is of course the original one, which is finding symmetry groups of differential equations in order to be able to reduce their order. So if you have a vector field and you have a flow which takes the vector field to itself, and that flow is transverse to the flow of the vector field, then in fact you can integrate your ODE by quadrature. But there's a lot of results, huge fat textbooks of results. So for example, if you have a second order ODE and the Lie group has a dimension 8, that means that there's 8 different symmetries, then in fact you can find coordinates such that your ODE is y double prime equals 0. And there's a lot of results, really a lot. So one big application of all of these results is, of course, automatic integration of ODEs using Maple and Mathematica and all of the like. And following on from that is the equivalence problem. Can you find a transformation which sends your ODE to an ODE that historically I know how to solve? That's a very big problem. So historically we know how to solve linear ODEs, and so a big kind of mini industry, that sounds strange, a big mini industry, is to find all the conditions under which, is to find the algorithm. If it's linearizable, find the transformation and find the target linear ODE. And we can do that. Recently people can do that. Alright, so if you look at these things, you'll see that this is a highly nonlinear condition and the previous one is a highly nonlinear condition, so you're not going to solve those in a hurry. But we can solve the linearized Lie group action. So, alright, what are we doing? So we've got here my Lie group. I've got my path through my Lie group, and I've got my vector field, my vector x, just a simple x here. One element of my Lie algebra, so the x is in my Lie algebra, one element of my Lie algebra gives me a vector field on the space on which my Lie group is acting. And I simply take this path here in the group and I use that to produce a path in my manifold, and then I differentiate that path. And so I have a map from the Lie algebra to the set of vector fields on M, which I'm denoting here as V of x. So I'm not very imaginative. So normally this is actually normally how you see the Lie algebra. This is how the Lie algebra usually comes out as the Lie algebra of vector fields in the applications. And then I have to show you how to get back to the Lie group. So what I get is a representation of my Lie algebra on the set of vector fields. So let's look at the example. And I say representation because we actually do get a representation. We do actually get the brackets go to sort of brackets. There's a map there. Anyway, let's look at our running example, which is our Möbius transformation, and I'm in SL2, so the determinant is 1. And so what do? Well, I take my condition and I take a path and I differentiate it. And so I get that, and my identity is of course that A and D are 1 and C and B are both 0. And so what do I get? I get that A dash of 0, I'm sure I fixed this slide before. This is better. I thought I deleted that slide. Okay, so what do I get? If I differentiate this, I get that A dash of 0 plus D dash of 0 is 0, and that those are both free, and so therefore my Lie algebra looks like that, which has simply got 0 trace, and that's the general element of SL2. So now let's do the same with my vector fields. So here we are again. I've got my path through the identity in the group, gives me a vector field, So what does this vector field look like? Well, there's my group element depending on t, and that's what I know about my element in my Lie algebra that this represents. And if I differentiate this, I hope you can see that because a dash of naught and d dash of naught have opposite signs, I get a 2 here. The b dash of naught gives me this beta, and if I differentiate here, down here, I get a minus u squared times gamma. And I've simply taken the derivative and multiplied it by du, and that's the standard notation for a vector field in first order differential operator notation. So that's as a derivation. I've written it as a derivation there. And so what I have is a map going from my h, my e in my, this is my little SL2, to here. I have a map to vector fields which goes like that. And so if I look at this, I have that my matrix Lie algebra is 3-dimensional in a 4-dimensional space, and my set of vector fields is a vector space over R. It's a 3-dimensional vector space over R sitting in an infinite dimensional space of vector fields. Yeah. So that's what I have there. Okay, so what about the bracket? So, well, here's my sum, and here's my image of them. This is the matrix bracket here of the matrix bracket, and now compare it to this. So this is the bracket of vector fields, which Hans talked about. So what is the bracket of vector fields? Well, as a derivation, it's v of w of f minus w of v of f, where f is a scalar. Maybe I shouldn't use f because Hans had f as the vector fields. What's a better f? What's a better what's a better function name for a function? Phi on phi. Okay. So if you look at this, you'll see that the second order derivatives always cancel. And in fact, all I really need to do is consider, when I'm calculating these things, is to consider that on the coefficients and take the reverse, because the second order derivatives always cancel. And can you see the link between the two brackets? It's not exactly the same. If it was exactly the same, that would be a plus 2u, and that would be a minus. So it's this weird little twist that we have when we go from the Lie algebra in the matrices to the Lie algebra on the vector fields, is that we introduce a minus sign, which is like this. So it is a Lie algebra homomorphism. It's linear. It respects the bracket. But why is it so? Why is there the minus sign? So I leave that as a puzzle for you guys. It's really interesting, hey? Anyway. So now let's look at the induced adjoint action. So what is this fabulous adjoint action that gave me my Cayley representation? What does it look like when I'm in the image of, when I'm looking at my Lie group as a transformation group? Okay, so this slide is thank you to Peter Hayden. I always do the right adjoint action, but for some reason I'm in a world on my own. Most people like the left adjoint action. So here it is. This is my action. I've called the result of the action u hat. I invert it like that. So I'm now changing, so I've got this du, and I have to change everything. I have to not only change my u's, but I have to change my operator part. So how does this work on a vector field? Well, I have to change d by du to d by du hat, and that looks like that. I'm sure you can all do the chain rule. So anyway, here is my general element, in the image of my Lie algebra, and I change my u's to u hats, and my du to my du hat, and I expand it all, and I collect terms, and that defines alpha hat, beta hat, and gamma hat. All right, that's what I get. If you actually look at it, that is what I get. And you know why it's so, why I'm guaranteed to get it, because the general principles that I showed you for the matrix Lie algebras, for the matrix groups, work here just the same. So I'm guaranteed to get this in the end up in the Lie algebra. And if I actually look at this, it's exactly what I get before. It's the same adjoint map that you get if you do it in the matrix version. The map that's induced on the coefficients is the same as what I got before. All right. Okay, so the discovery of Lie algebras were discovered as their images in transformation groups by Sophus Lie. He has 3 fabulous theorems, and the third one is that we can calculate the set of vector fields generated by the Lie group of symmetries of a differential equation, and this set of vector fields is a vector space. It's closed under the Lie bracket of vector fields, and this bracket is bilinear, skew-symmetric, and satisfies the Jacobi identity. So this is the origin of Lie algebras, and that's how they were discovered. So I've got a few minutes left, and I'll finish the story. I've gone from the Lie group to the Lie algebra by differentiating paths through identity. Now we need to finish our little story by going back the other way. So from Lie algebra to Lie group is the exponential map. So this is the definition of the exponential map on the left. That's the definition. You saw this in Hans' talk. If you have a transformation group, you simply have to integrate the vector field to find the flow lines with this particular initial point, and that will give you the Lie group action. And why is it so? Why is it so? So, there's 2 little questions here. You give me an element of any matrix Lie algebra, and that thing is guaranteed to be in the group. And I find that really quite mysterious. At least it's mysterious until you see why it's so. It's very easy to prove this relationship. You prove that by d by dr of e to the r e to the s minus r. You prove that oh, I need x. You prove these 2 things is equal to x e to the rx. If you prove those 2 things, then it's easy to prove that identity there. On the right, we get the equivalent identity. Now I've used gamma, which Hans called the phi. That was his phi star, and this is the flow lines. So these flow lines, these are the flow lines of this, if this vector field, and if you solve this, then these are the flow lines, and this follows directly from the existence and uniqueness of a solution of a first order differential equation, which is smooth enough. And the flow, so this is now, at least this was undergraduate for me. If you flow for time t and you flow for, you've got a vector field, you've got a river, the flow line, you drop a leaf on the river, the flow line is the path of the leaf, and if you flow for time t and flow for time s, it's the same as flowing for time t plus s. So that's a standard result. So, but in fact, to prove why you always end up in the Lie group, it's to understand that in fact what this is here is the solution to the same set of equations transferred to the Lie group. So they look very different, but they are the same thing in fact. So I take my vector here, I turn it into I either multiply on the right or I multiply on the left. And this gives me a vector field on G, and I take the flow line of this vector field going through the identity with that vector at x, and this is the formal solution of the equation the flow line has to solve, and that's why they're the same. So I think I'm going to stop there.